Okay, hello. So in class today, the pen was not working, but I fixed it. So in class, we did this stuff with typing math. If I can find my mouse. We did this stuff with typing math. And I think that might have been a little scary because I was jumping around and maybe it wasn't as good. So I'm going to redo it. If you didn't get anything out of the class, you can watch these videos and sort of get back into it. So let's do the first proof. Example 7. Prove that the limit as x goes to 0 of x sine 1 over x equals 0. What do you want to show? Well, we're given some epsilon greater than 0, and we want to show that we can find delta greater than 0 so that what? So that x sine 1 over x minus 0 in absolute value is less than epsilon whenever x is within delta of 0. So that's what we want to show. This is the statement for all epsilon greater than 0. There exists delta greater than 0 so that x sine 1 over x minus 0 less than epsilon, backwards 0, x minus 0 less than delta. Okay, and we're just going to connect like we always do. We're going to connect the hypothesis and the conclusion with a logical chain. We're going to start with the conclusion, x sine of 1 over x minus 0 is less than epsilon. Okay, so what are we going to do? We're just going to start by simplifying. This happens if and only if x sine 1 over x less than epsilon, x sine 1 over x less than epsilon, and now we notice that x sine 1 over x can be written as the absolute value of x times the sine of 1 over x. So that's good. That's good because we want to get to this thing at the end of the day. Absolute value of x is between 0 and delta, and we know we can always do this last step of connecting this to x is less than delta. So we're really close here because we have this absolute value of x in both where we are and where we want to get to. So the only thing that's annoying is this sine of 1 over x absolute value garbage. If there was a way we could get rid of the sine of 1 over x garbage, then we would be in business. And in class today, what we did is we had a lemma. So I'm going to do an aside here. A lemma is like a little side argument that you're going to use as part of your main argument, but you don't want it to get in the way of the flow of your argument. So you put it on the side, you prove it separately, and then you just say, by the lemma, this happens, and the proof of the lemma is separate. So the lemma in today's class was that the sine of 1 over x is less than 1.0001. So someone in chat wrote that. I think it's a great lemma. Why is the lemma true? This is the proof of the lemma. The proof of the lemma is true because sine of anything is always between 1 and minus 1. So sine of anything is always less than or equal to 1, and it's always greater than or equal to minus 1. And so by the sandwiching property, that is saying that the absolute value of sine of 1 over x is less than or equal to 1. And if you're less than or equal to 1, then you're definitely automatically less than 1.0001. That's the lemma. The lemma is saying no matter what happens, sine of 1 over x is always less than 1.001, and this is why the lemma is true. That's a lemma. How can we use the lemma? Well, if sine of 1 over x is always less than 1.001, that means that if you're looking at the absolute value of x times the sine thing, that's always going to be even smaller than x times 1.0001. So this stuff is always less than x times 1.001. Why? Because of the lemma. If this stuff is always less than this stuff, then this stuff will be less than epsilon whenever this stuff is less than epsilon. So we can replace sine of 1 over x in absolute value. That's the thing I'm underlining in blue. We can replace that by 1.001 because we know that sine of 1 over x is always less than 1.001. This rule of replacing something small by something big and having an implication error like this we gave that a name. We called that the left replacement rule. So the left replacement rule says you can always replace something small by something big as long as the arrow is going this way. And this happens exactly for the same reason that on the homework, I think there was a question that looked like this. If x is less than 4, then x is definitely less than 5. Okay, this one's going the other way. Let's do it like this. Epsilon is a secret number. Pretend epsilon is bigger than 5. If epsilon is a number that's bigger than 5, then epsilon is definitely bigger than 4. That was one of the homework problems with an x. So that's the left replacement rule. It says if epsilon is bigger than something big, then definitely epsilon is bigger than something small. And we're using it here with the big thing is 1.001 and the small thing is sine of 1 over x. So if epsilon is bigger than all this stuff, then definitely epsilon is going to be bigger than the thing with the sign. That's the left replacement rule. So we should justify it. We should say by the left replacement rule, left replacement rule, LRR stands for left replacement rule, and by the lemma. So the left replacement rule says if two things are in order, you can replace. The lemma explains why the two things are in order. Okay, now we're really close. All I'm going to do is move the epsilon to the other side. And now I can see what I have to do is I just have to set. Let's set. We're going to set delta to be epsilon divided by 1.001. And then absolute value of x will be less than delta. And that happens whenever absolute value of x is between 0 and delta. So with this setting of delta equals epsilon divided by 1.001, we've logically connected the hypothesis and the conclusion in the right way. And so we are good. We were given epsilon greater than 0. We found a delta. Delta equals epsilon divided by 1.001. That made this work. So that is the proof of example 7, in case something in class didn't make sense, which I probably didn't. So hopefully that helps.